Hey, welcome to section 3-6. We are talking about the chain rule. Um, if you remember from Algebra 1, when we talked about functions, we talked about all their operations. So we talked about how to add functions, we talked how to subtract, how to multiply, and how to divide. But there was another operation that we talked about, and that was composition of functions. So what happens when you put a function inside of a function? And so in calculus, we need to take all of these different operations and define how do we take the derivative of them. So we started by, simple power rules, addition, subtraction. We did the product and quotient rule. Well, today is the chain rule, and that's how do you deal with the composition of two functions. So, for example, I'm looking at maybe there's a function that's defined like this: x squared plus 3 to the fifth. This is really a composition of functions, because what's happening is you've got this kind of outside function, so to speak, that's saying we're going to take whatever's in here and take it to the fifth power. And then you've got this inside function right here of x squared plus 3. So I could kind of pull this apart into two different functions. Like, say this was originally f of x equals, well, let's not use f because we just used f. Like g of x equals x to the fifth, and h of x equals x squared plus 3. And so then you see that actually what this function is it's g of h of x. It's h plugged in here for g. So when we look at a function, we often talk about like what's the inside function and what's the outside function. And so we're going to start to be able to identify that in already composed form instead of these two parts like we did in Algebra 2. Okay, so into the calculus, how do we take the derivative of something like this? So let me define it in math terms, and then we'll do some examples. So let's say we define f and g to be functions, and we're going to define h of x to be the composition of the two. Okay, then the way we take the derivative of h of x when we have a composition is we take the derivative of the outside function, we evaluate it at the inside function, and then we multiply it by the derivative of the inside function. Okay, now I think being able to say that every time really helps. So it's the derivative of the outside function evaluated at the inside function, and evaluated just means plugged in. So that means that the inside function is plugged into that derivative times the derivative of the inside function. All right, that's the mathy term. Now let's do a problem, okay? Let's take this one that we defined up here. So we'll say define this function as x squared plus 3 to the fifth. Okay. The way that you first do this is you take, you got to figure out what the inside and outside function are. And we talked about that at the beginning. My inside function is the red, okay? That's my inside function. And my outside function is going to be green. That's the fifth power. So you ask yourself, okay, I need to take the derivative of the outside function. So how do you take the derivative of something to the fifth power? Well, I know how to take the derivative of x to the fifth, right? you drop the power and you lower by 1. All right, that's what the derivative is of that outside fifth power function. So that's what you're doing. You're dropping that 5, okay, and you're dropping the power by 1. Now, the reason I didn't put an x there and I put parentheses instead is because of the next part of this sentence. It says the derivative of the outside function evaluated at the inside function, which means plug in the inside function. So instead of an x here, I'm actually going to have the inside function here, which is x squared plus 3, my red inside function. Okay, so this is the 5 dropped in front, the lowered to the 4 is the derivative of the outside function. This is evaluated at the inside function, and now it says times the derivative of the inside function. Okay, well, let's look at that. The inside function is x squared plus 3. So the derivative of that is 2x plus 0. So I'm going to multiply by the derivative of the inside function. Okay, and then you can clean this up. These guys can combine a little bit. 5 times 2 is 10. And that's your derivative. This is f prime of x. Okay, and that's how the chain rule works. Now, I want to back off and do some simple examples, because here's the deal with the chain rule. We've actually been doing the chain rule all along, but you haven't known it. So let's start at the beginning here. We started with the power rule, the derivative of x to the 5th, or let's say to the 7th, all right? How do you take the derivative of this? Well, we said it's 7x to the 6th, right? But that actually isn't the entire story. What this is it's this is a composition of functions. The inside function is x, and the outside function is 7. Okay, so go through the words again. The derivative of the outside function, so that's the 7 drops down and lowers by 6, evaluated at the inside function, which means plug in x, times the derivative of the inside function. Well, what is the derivative of the inside function x? It's 1. So this is multiplied by 1. But that doesn't change the value at all, so it ends up being 7x to the 6th. See, so it's been happening all along. It's just that we've been multiplying by 1 up until now. So let's take a look at another example, another simple example, okay? Let's look at f of x equals sine x. So we learned a couple sections ago that the derivative of sine is cosine. Well, that's not actually all that's happening. What it is the outside, if I rewrite this function, and I'm going to color code it, the outside function is the sine. The inside function is the x. Okay, so let's run it through the chain rule verbiage. The derivative, so I'm going to take the derivative here, whoops. It's the derivative of the outside function. So what's the derivative of the red? Well, that's cosine. Okay, that's my derivative of the outside function. Now I'm going to evaluate it at the inside function, which means plug it in. And then I'm going to multiply by the derivative of the inside function. What's the derivative of x? Well, that's 1. See how that's actually the chain rule. It's just, again, the derivative of that inside function is consistently 1. Now let's compare that to, let's put some stuff in here. So let's say f of x equals sine of x squared now. How does this change the problem? Well, the outside function is sine. The inside function is x squared. And let's run it through the chain rule. The chain rule says the derivative of the outside function, so the derivative of the red, is cosine. And the trick is when you're taking the derivative of the outside function, don't ever write x. It's always like a blank spot, a parenthesis, a box, if you will. Okay? So you're just saying the derivative of the outside function is this derivative with a gap in the middle. That's what this spot is. Okay? Now I'm going to evaluate it at the inside function. So evaluate it at the green, which is x squared. That's what plugs into the spot. And then I'm going to multiply it by the derivative of the inside function. And the derivative of x squared, the green part, is 2x. And that's my derivative. Now, notationally, what helps a lot of students in this, I'm going to do the same problem, but I'm going to show you some different notation stuff. So a lot of times, just like with the product rule where we write d dx of the parts, like get the formula down first and then take the derivative, a lot of people do the same thing with the chain rule. So instead of writing this part first, let me just show you what people will do. They'll go through the chain rule and say, okay, it's going to be the derivative of the outside function evaluated at the inside function times the derivative of the inside function. And if that extra step is helpful, please do that. Then they take the derivative of that x squared and get their 2x. Okay? So that's how I'm going to kind of set it up for a while until we get really comfortable with this. But the thing that I really want to pound home is that every single derivative is a chain rule. So from here on out, I want you to think every time you do a derivative, I want you to think, I'm doing the chain rule. I'm doing the chain rule. It's just that sometimes your inside derivative might be 1. Okay? Because one of the most common mistakes in calculus is people will forget the chain rule. So they'll take the derivative of the outside function and plug in the inside function and not multiply by that last derivative. Okay, so with this example that we did, this one right here, you should now be able to pause your this video and try example 3.52. Okay, so do that, and then I'm going to do another example. All right, welcome back. If you did not pause the video, please do. There's no substitute for you guys working examples. Okay, let's do this problem. All right, I want to find the derivative of this. So, we're going to do the chain rule. Everything's a chain rule. So I have to identify the outside and the inside function. The outside function is tangent, and the inside function is 4x to the fifth plus 2x. Okay, so that's how my function is breaking up. And now I'm going to take the derivative. The chain rule says the derivative of the outside function. The derivative of tangent is secant squared. But I'm not going to write x, I'm going to write a space. Evaluated at the inside function, which means plug in the green, times the derivative of the inside function. And now I can actually do that derivative. Okay, and when we're dealing with trig functions, I really like it if this extra stuff is on the front, so we don't get confused that it's part of the secant. It's its own thing. Okay, and so this is our derivative right there. Okay, and with that example, you should pause and you should try example 3.53. Okay. All right, another example. Let me show you one thing the chain rule does here, and then we'll get back and do more product quotient combos. Let's look at this function. Once you get the hang of the chain rule, it's really powerful because it can eliminate the quotient rule, which is sometimes a bear. So let's look at this function. A simple rewriting of this changes it from a quotient to a product, or to a chain, excuse me, from a quotient to a chain. Remember, we learned this in Algebra 1 and 2. If you have something on the bottom of a denominator and you want to move it upstairs, or vice versa, upstairs you want to move it downstairs, you can do that, and all you have to do is change the sign on the exponent. So this squared, it can move up, but now it becomes a -2. And I've eliminated that fraction, so to speak, so I don't have a quotient rule anymore. I just have a straight up chain rule, which is oftentimes easier to manage. So if I break this up, my outside function is something to the -2. My inside function is 3x squared plus 1. So let's take the derivative. The derivative of the outside function. Okay, bring down the -2, lower the power by 1. That's what's happening on the outside function. It's a simple power rule. Then we evaluate that at the inside function, and we multiply by the derivative of the inside function. So I get 3x squared plus 1 to the -3 times the derivative, which is 6x. Okay, and if you want to, sometimes it's helpful. This changing these powers, negative, positive, and back and forth, is really a powerful tool. Please get used to that and do it often, because now it's really nice to simplify by throwing this piece back downstairs. So I'm left with a -2 and a 6x up top. These pieces stay upstairs because their powers are positive. And this one comes downstairs and it changes positive. So my answer is -12x over 3x squared plus 1 cubed. It will really help you algebraically if you can move back and forth between those. You start in fraction form, you move it up to negative, you do your calculus, and then you move it back to fraction form. Okay? So that's a shortcut, and really you don't ever have to do the quotient rule again if you use this trick. Okay, you can choose between the quotient or the chain. All right, let's do some mix and match. This section is worth your time. It's really a critical section. This is one of those that I would definitely recommend working more problems than are assigned and going into the book and doing some extra problems. So here's a combination of a product and a chain. So on the onset, what I see on the very outside vision is this is two things multiplied. Okay, that's the first thing. Now, yes, there are some powers on here and there's some chain rules going on, but they're kind of in parts of the problem. Overall, what this function is it's two things being multiplied. So I start with the product rule. So let's write that out. The derivative of the first term times the second term plus the derivative of the second term times the first term. Okay, I really think it's going to benefit you to write it out like this in pieces, because look at now what we have. This part, this derivative right here, and this derivative are chain rules. You've got your outside function right here and here, and you've got your inside functions here and here. So let's do those derivatives really carefully here. The derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, so let's mark this. This piece right here is this right here. That's your chain rule. Then I've got times the 2x plus 1 to the fifth and plus, now let's do this derivative right here. This is also a chain rule. The derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, keep running out of room here, sorry. Scooch over again. Okay, that is this piece right here. And then multiplied by this 3x squared plus x to the fourth. So you see how it's really easy to lose track of things, okay? That's why having these steps with the derivative markations as you go along, I think is really helpful. So now let's go through and do our last step of derivatives, this piece and this piece. So I've got 4. The derivative here is going to be 6x plus 1. And the derivative here is just 2. Okay, now how do we clean this up? The fastest way to clean these things up is kind of like the quotient rule. You're looking for factors that you can factor out. Look at what's happening. I actually have one big term right here and one big term right here. So what do they have in common? I see that they have 3 of these each, and they have 4 of these each. Okay, let's start with that. They also have a factor of 2, but let's start with those guys and see what happens. So I'm going to pull out 3x squared plus x cubed. Okay, because I'm looking at these. This has 3 to give, this has 4, so 3 is the max I can pull out. And then my 2x plus 1s, this has 5 to give and this has 4, so I can only pull out 4. Now, let's see what's left. I pulled out all of this and I pulled out 4 of these. So what I'm left with is a 4, a 6x plus 1, and 1 of these 2x plus 1s. Okay, that's my first term, what's remaining. My second term, let's see what we pulled out. I pulled out all of these, and I pulled out 3 of these. So I'm left with a 5, a 2, and 1 of these guys. Okay, And then often what you have left here is easier to manage. Instead of trying to multiply out something to the fourth power, I'm just kind of foiling out a couple things. Now, you may look at this point and say, hey, I've also got a factor of 2 here. Okay, so I could also pull a 2 out in front. And that takes this away and leaves a 2 here. All right, so let's rewrite that. We've got 2 times 3x squared x cubed okay, and now I can focus on my brackets and multiply some things out. This is going to be, let me do it this way. This is going to be 12x squared. I've got a 6, 7, 8x, and a 1. So if I distribute this 2 into that, I'm going to get 24x squared, 16x, and a 2. And then the 5 distributes in here. 15x squared, 5x. Okay, and the advantage of doing that is you're going to have a lot of like terms. So this is going to become 2, 3x squared x, 2x plus 1. And then I'm left here with, let's see, 24 and 15, that's 39x squared. And this is going to be 21x, and this is a 2. All right, hopefully I made it through that without a typo, but this is your derivative. Okay, so these can get pretty hairy, so just take your time. My biggest suggestion with this is taking the time to write out these steps where you write the derivatives partway through, and make sure your writing's neat, lay it out clearly, and copy correctly. Okay. If you'd like to, pause and try one of these. I think example 3.54 would be good to do now. Okay, I'm going to do another example. I feel like I can't do enough examples of these because it's so critical. This is an interesting problem. One of the reasons I want to show it to you is because I want to remind you of something we learned in trig, which is trig functions notationally have this weird thing. We put the power right here between the sine function and the angle. And I want you to be aware that this notation really is saying this. That's what it means, okay? And it's important because some people look at this and say, when they look at this form, they say, oh, sine is the outside function. And it's actually not. This 6 is the outside function, okay? So let's do the chain rule on this. The outside function is 6. The inside function is this sine x cubed. Let's run it through. The derivative of the outside function evaluated at the inside function times the derivative of the inside function. Now check this out. This derivative right here is another chain rule. So the outside function now is sine, because there's no more power, and the inside function is now x cubed. So let's do that derivative. This 6 sine x cubed to the 5th comes down for the ride, and here we go, derivative of this, derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay. I'm going to change this notation and write the fifth power right here where we usually write it. And the derivative of x cubed is 3x squared. So I'm going to bring that up front so I don't get it confused with my angles. And that's my derivative. Okay, so that's the example of, like, I call that a chain inside a chain. Okay, you could try example 3.55 now. And I'm going to do one more. Okay, there's two ways to do this problem. One is to identify that this as the outside function and this as the inside function. The other way is to break up the power and make this x to the fifth over 3x plus 2 to the fifth. And then it becomes a quotient rule first with a chain rule embedded. Or you can bring your denominator up and make that power negative, and now it's a product rule first with a chain rule embedded. So it just depends on your flavor, and it doesn't matter to me which way you do it. I'm going to do it this first way. It's not actually the way that I would do it. I would probably, if I was on my own, do it this way. I don't like the quotient rule, so I try to break things up and eliminate that as much as possible on the front end. But this is the way that most people see it, so I'm going to go ahead and do that. It's a chain rule first. There is a quotient, but it's inside. So first off, I'm seeing this power on the outside. So the derivative, now this is notation. When it's y, we don't put y prime, we put dy dx. Okay? The different notation. Okay? And the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, now this is a quotient rule. So I'm going to keep this along for the ride. If you don't recopy it every time, chances are you forget it at some point and don't tack it onto the end. So I would recopy every time, even though it's kind of a pain. Quotient rule here. Low d high minus high d low square the denominator, and away we go. So let's see how this cleans up. The top, I've just got 3x plus 2 minus 3x, so those cancel, and I'm just left with a 2 on top and a 3x plus 2 squared. And because, well, it's fine. These could multiply together. Because it's all multiplication, you don't need a common denominator. But this is fine for me. There's, to me, my rule of thumb is if something might cancel, it's worth simplifying. But I can see that all that's going to happen is these numerators are going to jam together, these are going to jam together, but nothing's going to cancel. So this is a fine way to end. Okay, so that's an example of a quotient rule with a chain. And in this section too, in the homework, just be aware, in every section we do this, I might ask you to find the equation of the tangent line at a certain point, whatever, I don't know, 2, 5 or something like that. And if that is the case, you plug in your x value and get your slope, and then write the equation of the line. So don't forget that that's there. This point won't work with this problem. This is an example. So you're going to plug in your x value to find slope, and then write your equation of your line. We've done that a lot, so hopefully that looks familiar. Okay, good luck. Try some of these, and make sure you do lots of practice in this section. Thanks for